All right, linear regression is going to tell us how well data fit a line. Bivariate data means you have to have ordered pairs. Your data is in two variables. Pearson product moment correlation coefficient R is is a tool that lets us know how well it fits. Then we have a scatter diagram, which if you're going to do linear correlation, you're going to definitely need a scatter diagram because that lets you look at the data to see how linear it is. We're going to do lines of best fit. All right, we're going to look at the mathematical and contextual interpretation, which is what you'll need to do in your IA, equation of the regression line of y on x, and then use it for prediction purposes. All right, so we have a population, which is all the measurements of interest. We have a sample, which is a portion of the population or a subset. A subset would be a subgroup. Our class is a subset of all the students at PHUHS. That's what we mean by subset. So when we talk about bivariate analysis, we're looking at relationships between pairs of variables x and y. For example, height and weight, ounces of water and the height of a plant, number of hours on social media, and your test score. I think some people are looking at that too. All right, a scatter diagram or a scatter plot is a graph of your data. So if you can get your data into your calculator in X1 and Y1, then all you have to do is turn your calculator on. I would strongly urge you to use Excel. Excel, you can do scatter plots, and Excel will allow you to do the calculations that we're about to do. All right, so the scatter plot is used to see possible relationship between the two variables that relate to the same event. I don't think it was this class. I think it might have been C-Day. Someone came to me with some information, and I said, is it even a relationship? And once they got their data and they plotted it, you see how this at least is kind of going down in a line. There's a little bit of variance. Theirs was all over the place. So that let them know that that probably wasn't a good, that they needed to change what they were going to look at to find something that maybe was more linear. And this person did and came up with a much better relationship. Correlation is a relationship between two variables. It does not mean one caused the other. It just means there's a relationship. It can be positive, it can be negative, or there can be no correlation. It gives the linearity, determines if the points have a linear trend, and it gives the strength, strong, moderate, weak, or none. So that's what the R does. The R will tell us whether it is going up, whether it's going down, whether it's strong, moderate, weak, or none. All right, so next, a general upward trend in the pattern of the dots is a positive correlation. This is an example of a positive correlation. The value of the dependent variable is always your y. It depends on the changes in the x. So the y's are getting bigger as x gets bigger. So as we move to the right, the y values are getting bigger. That's an upward or positive trend. A general downward trend in the pattern of dots shows a negative correlation. What this means is your x's get bigger, your y values are decreasing. So as you drive more miles, your gas tank, the level of gas in your gas tank is going down. So the dependent variable is getting smaller as your independent variable is increasing. So these are things that you would want to talk about if you're doing data and doing correlation. So scattered plots or scattered points with no trend, they're all over the place. It would be a correlation close to zero. That is not a linear relationship at all. So the scatter diagrams will allow you to kind of eyeball the strength of a correlation. There are mathematical techniques that allow us to do it a whole lot better. All right, so what do we have? Nothing more. This is a strong positive correlation. This is a moderate, and you see how they're more spread out, not quite as linear, positive correlation. And this is low, this is high, we're going upwards, it's a lot fatter. This would be a weak positive correlation. Here is a relatively strong negative correlation. There's a moderate and there's a weak. So one of the things you want to do is graph it to see even if there's a correlation that you want to explore. Not all relationships are linear. That approximately looks linear. This does not. And, you know, one of the options is to not fit a linear equation, but to try to fit a curve equation. There's a lot of math with the linear, and that's why they put it in here. But be aware that everything's not linear. Now, causation. Correlation does not mean that one causes the other. For example, shoe sizes of grade school students and their vocabulary have a positive, strong correlation. In other words, the larger the shoe size, the larger the vocabulary of the student. Now, what's happening as the shoe size gets bigger? What's happening to the child? They're getting older, and as they're getting older, what's happening? Well, they're going through the grade level. So does it make sense that because they're gone from first grade to fourth grade that their vocabulary should increase? Doesn't mean their shoe size caused the increase of relationship. The confounding factor is age. So just be careful when you are working on your IA that you don't say one causes the other. So this is where we can put in, and maybe we should get, now again, on an IA, I would use, now as you explore, you might want to use your graphing calculator, but you're going to need the data tables, you're going to need the scatter plots, and you're not going to be able to do this sketchpad. Excel will allow you to copy the file, put it into a document. All right, so let me get my calculator. We're going to view on top. All right, so we're going to go here and we're going to put in data. I think you all know that you go to stat. We're going to go enter. And then we've got one. I can do this so much faster if I'm at the keyboard. So we've got 1, 2, 3, 4. Oh, that's 4, yep. And then we're going to go to list 2. All right, so then we want to go to second y equals to turn our stat plot on. We're using list 1, list 2. We go graph. I'm going to zoom. Did I turn it on? Oh. So now I'm going to go to my stat plot and I'm going to turn it on. There we go. How's that? Is that better? So if I go to, there is a zoom stat feature, and it centers your window on your statistics. So what would you say that is? Positive, strong, moderate, or weak? Moderate. They'd probably consider that strong, yeah. All right. So that's one of the things you're looking at. All right. So here's some practice. This would be, I'd probably say, they might say moderate, and they might call this, they might, yeah, it's amazing what they'll call moderate. So this is definitely weak. This is definitely weak. These are going to be probably more moderate. That is going to be a, yeah, 0. All right. So now this is a line of best fit. This is what you would be finding. It's a trend line is drawn on a scatter diagram to find the direction of an association between two variables and to show the trend. This line of best fit can then be used to make predictions. So notice X bar, Y bar. That's going to be an important point, so remember that. That's the mean point. That means the mean of the X's and the mean of the Y's. And how do you find means? How do you find a mean? Add them up. Divide by the number of numbers. So to draw a line of best fit, you're going to eyeball, let's see, you can eyeball it. That will balance the number of points above the line with the number of points below the line. So if you're doing linear regression, by all means, feel free to draw in your own line, calculate your line, and then compare it with your actual regression. Improvement is to have a reference point, and the reference point is the mean point. So maybe you want to calculate that mean point and then draw your own line of best fit and then do your regression. All right. So is there a relationship? We find the mean of the number of grams of fat, find the mean and the number of calories, construct a scatter diagram, plot the mean point, and use it to draw a line. So the mean point is not necessarily a point that's actually here. Does that make sense? A mean point is a point that you have created. So this is a big data set. So let's go back to our little data set. So how would we do that? Right, so I'm going to be lazy, and I'm going to go to my calculator, and I'm going to go to stat, and I'm going to go to calculate, and I'm going to do one variable statistics, and I'm going to do it on my list 1. Okay. So what is my mean? 4.7. And then I'm going to, but you're going to, if you're doing linear regression, you will do this by what? Hand, 1 time. Okay? And then I'm going to go back over here. I'm going to go to calculate maybe. What did I just do? Come on. And I'm going to do one variable statistics again, but this time I'm going to do it with list 2. So I get my y bar. And my y bar is, it looks like x bar. It's going to be 5.3. So did I put my numbers in? So now I think what I would do is, if I want to graph it, I'm going to go here, and you would have Excel or whatever. You would plot this point, and so now I will have my mean point in. And this is if I were going to do draw my own regression line, then I would want to make sure, now I don't know which point that is, but I would want to make sure that might be that one, that my line, that I use that as one ordered pair, and then I use another. Okay? So far, so good? All right. So I've got all these examples. Table shows relationships between interest rate and the price of a home. Find the mean point. So here's your interest rate, here's the price of a home. Construct a scatter diagram and draw a line of best fit through your mean point. Comparing the interest rate and the price of a home in 2016 with, let's say, the interest rate and the price of a home in 2010 or 2009. Why would that be interesting? What happened in 2009, 2010, 2011? 2008. Oh, there's a big market crash in the real estate market. Okay? So interest rates were at an all-time low, and housing prices were at an all-time low. So that would have been an interesting IA. All right. Table shows the price of a house and by square feet. And a lot of times they will get the price of asking price based on square feet. Find the mean point, construct a scatter diagram, describe the correlation, and then what can you say about the square feet? All right, so now, the equation of a line of best fit through the mean point. Raw data rarely fit a straight line exactly. You must be satisfied with rough predictions. Typically, you have a set of data whose scatter diagram appears to fit a straight line or line of best interest. That is called your regression line, the line of best fit. Now, this is important for those of you who are doing this. A regression line can be used to predict values within the data set. It's called interpolation. So let's go back a minute. Let's go back to this data set. Let's see, price in square feet. So your square feet here starts at, your lowest is 1,100, and what's your highest? 2,400? Does that look right? 2,450? All right. So you're going to find this regression line, and you can use this line to predict what a house should sell for, as long as the square feet are between 1,100 and 2,450 square feet. What if you want to price a house that is 2,800 square feet? This is not as good. The line fits the data in here. You with me? So let's say you need to list a house that has 1,900 square feet. So you would put into your equation 1,900 and see what you come out with. But this might not work for 28. That's what we mean by interpolation. You're within the data. Extrapolation, no, extrapolation. I thought it was extrapolation. I'll have to look at that up. I think it is extrapolation. Extrapolation means you're going beyond the data set, and it is not as good a predictor. So just be aware, if you are going to look at errors outside your range, that it might not be very accurate. Okay, I'm going to continue, and you all can take a break when we're done. It's up to you. All right, so let's look at how we're going to do this. Find the regression for home examples. All right, for children between the ages of 7 and 28, the time for a child to run 1 kilometer is decreasing an average rate of. So at this point, what we're looking at is we want to interpret the slope. All right, so a study was done. This investigates the relationship in age of a young person and the time it takes them to run a kilometer. They collected data from ages 7 to 18. Now, this is a y-intercept. That means at time 0, the child can run, what is y? Minutes. It takes a child 20 minutes to run a kilometer. Now let's think about that. At year 0, what's the age of the child? Newborn. Okay? So the y-intercept a lot of times doesn't make sense. So this line is going to be good from 7 to 18. So when you interpret slope, for each x, the y is increasing or decreasing at an average, and we did this in calc. It's got to be average because it's Algebra 1 slope, rate of blank blank units. So if we were looking at this, it is 0.5 kilometers. That was our slope. It's negative. It's decreasing. So for the x's, for children between the ages of 7 and 28, the y, which is the time for the child to run 1 kilometer, it's negative, decreasing at an average rate of 1/2 kilometer per year. So you're probably going to want to interpret your slope. The interpretation of your y-intercept will always be 0 x units and y units. So when the child is first born, actually a newborn, the child takes 20 minutes to run 1 kilometer. That makes no sense because the child cannot run. The child cannot stand. The child cannot hold their head up. So, you know, sometimes it might make sense, many times it will not. The function below shows the cost of a hamburger with different choice of toppings t. So t is the number of toppings. So if we wanted to interpret this, then we would say that as the number of toppings increase, I should say, that the price. Let's do this one first. Biologist wants to study the relationship between the number of trees, x, and the number of birds, y. She calculates the regression to b. So I've got 5.4, and that's going to be y over x, because that's how we do slope. So this is going to be birds, and this is going to be trees, because that's my x. So for each increase in one tree, the number of birds in that hectare is increasing 5.4 birds per tree. For each additional tree in our area, approximately 5.4 more birds will be in that area. Here, this is T is toppings, and this is going to be dollars. So for each additional topping, the price of a burger goes up $1.40. Okay, so X is in miles, Y is what? What he paid. So we've got 1/2, this is going to be dollars per mile. So it would make more sense to do 0.5 over 1. So for each additional mile, Charlie is paying 50 cents. So you need to be able to interpret your slope. All right, another way to improve is residuals. All right, this is where we start to get to be the regression line. This beautiful little regression line wants to make the distance from the point to the line as small as possible. We want to make these distances as small as possible. All right. So they call slope gradient. So the slope of the regression line is going to be sxy over s of x squared. Just means the sum. So if I want to find my numerator, I'm going to take the sum of the product of my x times my y and subtract from that the sum of the x's times the sum of the y's divided by the number of numbers I have. This is where your Excel spreadsheet is going to be beautiful. So then your denominator is going to be, this is going to be the sum. You're going to square your x's, then you're going to add them up. Then you're going to add all your x's and then square it and divide it by n. So here it tells us, means the sum of all the products of xy, means the sum of all the x's, means sum of all the y's, means sum of the squares of the x's, means the sum of the x's, then square the result. So this is where your Excel spreadsheet comes in. When finding the least squares regression equation, you'll find the slope and you'll use your mean point. So if we want to do this, use least squares regression formula to find the equation of the regression line through these points. So the first thing we're going to do is we're going to multiply 2 times 4 is 8, 3 times 5, 4 times 8, 32. Square, 2 squared, 3 squared, 4 squared. Okay, sum of each column. 4 plus 3 is 7, 8, 9. We've got 13 plus 4 is 17. 32 plus 8 is 40, 55. 4 and 16 is 20, 29. So how do I get x bar? Do I have the sum of my x's? Do I know how many x's I have? So we get 3. Do you see how sweet that table is? Y bar, do I have the sum of my y's? And how many y's do I have? 3. So your point that you will use for writing your regression equation is going to be 3/17. And my suggestion is you don't use a decimal, you use the exact value. All right, so do I have, let's see. Let's go back. So now what I'm going to do is I'm going to come back here and I am going to take all this. And I'm going to copy it and it's going to be really big. And then I'm going to paste it and I'm going to be sorry. So I'll move, oh darn, we got that already. I think I can get rid of that. Oh, this is what we need. All right. So what we're going to do now is we're going to compute our xy. So do I have the sum of my x times y? What's the sum of my x times y's? 55. From that, I'm going to subtract. What's the sum of the x's times the sum of the y's divided by how many numbers do we have? I think it's going to be 3 because they're ordered pairs. So I need someone to get out a calculator. So 55 minus, what's 9 times 17? Negative 98, so I'm going to make that positive 98 over 3. Oh, wait a minute. 153, and that's supposed to be a minus, isn't it? Okay, and so what is that going to be? You figured that out, I think, already. Positive 4? Oh, that was nice. Okay, so now let's do this one. Do I have my x squared column? That's the last column. What are the sum of my x squareds? Use a different color. We've got 29, okay, minus, this is my x sum column, correct? So that's going to be 9 squared over. So that's going to be 81 divided by 3 is 27, or 2. So what are we supposed to do now? We're supposed to take our SYs, which is 4, divided by this, which is 2. What's the slope of my regression line? 2. Oh, did I square it? Oh, just kidding. Wait a minute. S of x squared is the sum of the x. I think I'm okay. Okay, so now what we're going to do is we are going to find the equation of the line. There's my ordered pair. There's my slope. So we'll say y, and we might not, yeah, minus 17 thirds is equal to 2 times x minus 3. So you've got y is equal to 2x minus 6 plus 17 thirds. Do you agree that's 18 thirds? 18 thirds negative plus 17 thirds is minus 1/3. That would be your regression line. Did we plot this data on our calculators? I don't think we did. All right, so let's go back into stat. I might be sorry that but I'm going to clear these lists. What I want to do is see how close we came. Clear. All right, so I'm going to enter 2, 3, 4. And then I'm going to come over here and now I got a positive slope. Does it make sense I should have a positive slope? Why? As the x's are getting bigger, the y's are getting bigger. All right, so let's graph these points. All right, so now we're going to go over here. What was our equation? We're going to type in 2x. All right, so the 2's on the wrong side. Minus 1 divided 3. All right, so let's see how well it fits. Now what we're going to do is we're going to go to stat. We're going to go over to calculate. We're going to do the linear regression. And oh my gosh, look at that. It's the regression equation. Was that too bad? Do you see how you can have Excel? You can type in one column, type in the another, and the next column tell them to multiply them. Next column, tell them to square the x's. You with me? Down here, you can tell them to sum your columns. So Excel is a great way to do it. Okay, so there's another practice. So we just did our graphing calculator. All right, so now let's look at R, because you're going to want to find this. This is a measure of correlation between variables x and y. It gives you a value between +1, meaning positive perfect correlation, -1, meaning negative perfect correlation, 0 meaning no correlation. So this R correlation is going to tell you how strong of a fit. So this is important, this slide. R squared explains how much of the variation in the values of y are explained by the least square regression line of y on x. So R squared would explain how much the variation in the price of the hamburger is. Let's see, how much the variation in values of the price of the hamburger are explained by the least square regression line of the cost of burgers on the toppings. R tells you how strong of a linear relationship the data have and the direction of that data. So correlation is a relationship between, we already did this. So now this gives you some idea numerically of what we're looking at. 0.75 to 1, we do absolute value because we don't care whether it's negative or positive. Strong, 50 to 75, moderate, 25 to 50, weak, and 0 to 25 is very weak to none. So here are some data sets. This was a correlation of 0.7, which is a little bit below strong. This is a 0.3, which is a little bit on the upper end of weak. So this is what we did, correct? So now my R is going to be the sum of my, or the s of xy, which we already computed, and then s of x and s of y, and those are the new ones. So I wonder if I can bring my data table. Probably not. Okay, so let's go ahead, and I think what we're going to do here is we're going to now do the correlation coefficient. So I'm going to need someone with a calculator. So we need 120 times 26. 3,120. I need 120 squared. Okay, I need y squared. Okay, so if you're doing linear regression, we already went to here, correct? So to include your r, you have one additional column. All right, 187 squared. What? JK. Should be there. Okay, what's third? I can do 30 squared. How about 187 times 30? $109 times 26. $109 squared. All right, 103 times 24. X squared? 24 squared? So now we need the sum of the x's. We need the sum of all those columns. Okay. 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 All right, so I don't think we can see what this said. Ninth grade boys at Webb School go on a backpacking trip each fall. They're divided into hiking groups the size of 4 by selecting names from a hat. Before leaving, students and their backpacks are weighed. The data from one hiking group is below. All right, so we're going to find the correlation coefficient, but in order to do this, we need this information over here. So this is the R. So let's go over here and see what we've got. So the first thing we're going to do is we're going to find S of xy. Do you remember what that's? I don't remember that. There it is. All right. Paste. So what we need our data. So I'm going to do this up here. We're going to move these down here. All right. So we have the sum of our xy's, correct? So that is going to be 14,036 minus the sum of the x's, which was 518, times the sum of the y's, which is 106, divided by, how many numbers do we have? 4? Okay, can you figure that out for us? 309? Okay, so my numerator is going to be 309. All right, so now what we're going to do is we're going to find the sum, we're going to do the square root of the sum of the y's, which we have to be 28, 28. Yes, that's the sum of the y squareds. Minus, now we need the sum of the y's. There's the sum of the y's, and we need to square that, which is going to be 106 squared all over n, which is 4. And what would that be? Is it, have you square rooted it?
Yes.
Okay, tell me what's under the root. Okay, and what is that? In a fraction form. Yeah. That way we won't have rounding error. And that's something you want to think about on your IAs. You don't want a rounding error. 19, is it? Nice. Okay. So we know that this is square root of 19. So now we're going to need the sum of the x squared column, which I do believe was 71859, minus the sum of the x column, which is 518 squared over 4, and then all that's going to be square rooted. Boy, that's a bigger one, isn't it? 4778. 4778. So this is going to be the square root of 4778. So now we want to figure out, get a different color. We want to figure out what is 309 over the square root of 4778 times the square root of 19. That's my R. What is that? Yes, now we want the final decimal. What is it?
1.0.
Okay, can we have something too big like that? No, our R has to be between 1 and -1, so we messed up somewhere. Pardon? This says R, that says that's R. Doesn't say it's R squared, so let me double check and make sure I didn't type my notes wrong. This is chapter 10. All right, summary. Let's see if they've got the formulas in the summary. All right, R is the sum of xy over sum of x times SOY. So we did something, let's go back and check our math. We did something wrong in our calculations. I guess I could check those other formulas too. And maybe it's something that I wrote down wrong. So I'm going to pause this while we find our mistake. All right, we found our mistake. And what is amazing is 1 unit right there caused everything to be off. So those are our new figures. And what we got this time as our correlation coefficient was 0.96413. So describe the strength. Is that how strong, moderate, weak? Strong. Direction? Positive. Interpret the correlation. What does this mean? This means that 96% of the behavior in Y's can be attributed or is linear or linked to your X's. So what do we have? Let's go back. Where did we start? So R squared explains how much the variation in the values of Y. So 96% of the variation in the is explained. All right. So what do we have? 96% of the weight of the backpack, I guess, variation in the weight of the backpack to the body weight is explained. So does that mean that the body weight causes the backpack weight? Or the body weight causes the backpack weight? However, is it possible that the more you weigh, the more you can carry? Okay, so there is a 96%. And that is linear regression. Did that help? Was it worthwhile?